I'm seeing the presentation.
Okay, perfect. So as Oscar said, I'm going to talk about, actually what I'm going to talk about today is cloud native supercomputing, a new program that we've started in NVIDIA around combining isolation, both from a security perspective as well as performance perspective, and other ways too, with bare metal performance in a cloud native type of environment. So providing cloud-like services in the context of bare metal performance, bare metal performance in a variety of pieces. So I'm going to talk today specifically about the network side of things, but there's more than just the network side of things as part of this effort. It's an end-to-end effort, starting with GPUs, CPUs, a full system type of operation. So what I'm going to focus on is really the piece around supercomputing. Obviously, we support a wide range of setups now that computing has gone to a lot of different locations. Edge, with a variety of real-time processing, traditional HPC, AI, and a number of other type of scenarios. So I'm going to really focus today, or actually, Gitina and myself are going to focus today on the HPC side of things, and specifically in the context of the cloud. So from a hardware perspective, again focusing on the network side of things, what we have connecting all these parts in the generation of technology that's coming up are three key pieces from the network side of things. We have the quantum 2 switch, which is a high performance switch, 400 gigabits per second, 64 ports of 400 gigabits per second, or 128 ports of 200 gigabits per second. So it provides high bandwidth connectivity between nodes in the network for scale out type of operations. We have from a connectivity from the host to the network side of things, there are two pieces that contribute here. One is just the generic HCA, which is the Connectix 7 InfiniBand adapter, and actually the one that's of interest in the context of the cloud native supercomputing effort is the Bluefield 3 system on a chip, which is a combination of a Connectix 7 adapter, some ARM cores, specifically 16 ARM cores, and several accelerators that are aimed at both security and storage for the most part. So this is the base hardware that's targeted specifically at dealing with these sort of security issues. So from a end-to-end communication stack, so both hardware and software, there are a couple of ways, there are several different ways to describe the sort of support that we provide for this. First of all, there's the side that's just raw capabilities. You talk about, so it's high bandwidth, low latency, high message rates, and certain capabilities that let us scale out well, such as first of all RDMA or GPU direct RDMA, as well as GPU direct storage, features that help improve network efficiency like adaptive routing and congestion control, as well as a variety of topologies that let you adapt you build systems that fit your needs, whether it's needs in terms of raw performance, needs in terms of costs and the like. But these are the base building blocks that are used to build the system. So one of the things that, as people know, especially people on this call, is one of the big emphases that we have in NVIDIA and before that in Mellanox is around putting compute where it belongs. And specifically, since we're talking about the network, the pieces of compute that we're talking about are pieces of compute that fit somewhere within the network. And these include, for example, things like MPI tag matching that help accelerate tag matching. This feature is in the HCA. Other features in the HCA, HCA/Bluefield include a new optimization for small data all-to-all, so you can get close to wire speed for those very tough operations. We also have elements in the host channel adapter, specifically RISC-V cores that are well, in the HCA itself, the RISC-V cores that can be programmed mostly for control type of operations, but they're user programmable. And we also have on the card itself ARM cores, A78s, if I remember correctly, that are programmable with your standard compilers, run Linux and the like, so you have the ability to run code on those ARM cores. And so that's where we take advantage of those capabilities, for example, to help with security, help with offloading communication, and the like. So in the network itself and the switches themselves, we have two pieces that are relevant here. One are the data reductions, or SHARP, that accelerate data reduction. We also have a capability called Shield that's a autonomous approach for getting around problems in the network. Links that go down, switches that go down, and the like. And as I indicated, these are some of the things that can be used to build our data security and tenant isolation. But definitely not the only pieces, but pieces that help run that. So a bit about the DPU or the Bluefield adapter. It's really the piece of hardware that's at the core of these capabilities. As I mentioned before, has several pieces to it. It has it's a system on a chip. It has within it a host channel adapter, the ConnectX adapter. It has a PCI switch, some programmable ARMs, acceleration engines for storage and security mostly, as well as some memory. So this is really the piece that lets when it's run in security mode, when it's run as part of the Cloud Native Supercomputing initiative, it's inaccessible. Users can't get into it, and so it provides a means of isolating, gives a means of isolating security type of operations to that unit, not allowing users to get onto it. And so if someone manages to, for example, break into to one of the hosts or something like that, the damage is localized. From a design perspective, a few things that are just a really high level cartoon about the differences between how cloud native supercomputing infrastructure is different from your traditional supercomputing, the one we're familiar with so far. First of all, in traditional supercomputers, the host is the center of activity. So the application runs there, your communication library is there, your storage runs there, any sort of security management isolation also will run there. And so there's cycles taken away from the application to do this these sort of operations. And also the fact that its security, for example, runs there means that it's running in the same domain where the application is running. And so once you've broken into that system, you have quite a bit of free reign in the system and can do quite a bit of damage. In cloud native supercomputing, services are migrated or can be migrated down to the Bluefield. As I indicated before, the Bluefield, when it's run in that mode, is inaccessible to users. It's on its own administrative subnet, so you can't get in. So it's hard to get into. Services such as communication library and storage capabilities, as well as security management or system management capabilities are being moved down to the blue field, with the goal of leaving the host for compute, leaving it as much as possible to the application. So in the zero trust architecture, several things happen. So one, storage. So as I already talked about the security aspect of it, where the security management happens in the blue field, and it happens on a per job basis. It's the one that's the place for one, for example, sets up, gives access to network access to the application, so the application can't necessarily on its own just try and access the network. It has to go through that capability. This piece is not yet implemented, but that piece is in the works. Storage is a piece that's been worked on the most, so mounts and the like are granted in the on the blue field, the request from the host, and there's work going on right now and using Vert.io to basically forward the storage request to the blue field from the host, and move that workload there, as well as the security in terms of access down there. That's where there are also capabilities that have existed for a long time in InfiniBand that lets us give certain levels of guarantee level, certain guarantees on tenant service levels, and it can, and these capabilities are support a very large number of isolated users on a single subnet. From a performance perspective, as I indicated before, there's work to move down application communication library management to the DPU, aimed in particularly at supporting asynchronous communication model. This is independent of other accelerations that already happen but this is an addition of other accelerations that already happen in the host channel adapter itself. And in security mode, of course, the only pieces of software that are allowed to run there are well-vetted pieces of software. Users can't just on their own decide to put these in. So some of the things that are being looked at offloading to there are things like the collective operations. I believe you've heard about the active message support it's been added to UCX. In general progression of asynchronous operations, and you can think of other things you might do, user-defined algorithms, user-defined applications and the like. So some of the efforts that I'm familiar with are going on now, for example, involve moving application control path type of operations down to the DPU. So things like load balancing and the like, moving that down to the DPU. And other things are being looked at by a variety of people. So moving the collective communication support down to the network, the asynchronous support down to the network is an obvious first attempt. So DK Panda's group at Ohio State has done work on the several non-blocking collectives here. You can see the performance data here from all to all gather and broadcast, and they've shown some nice improvement in performance, in the performance of these algorithms by moving the progression down to the DPU. And also, of course, what this is really targeted at is overlap. One of the things, and this sort of acceleration, no surprise, provides good overlap. Both in primitive tests as well as in a simple FFT test here, where there's on the order of, looks to me like about 20% application performance by moving the, I think it was the non-blocking all-to-all down to the DPU. There's also a software infrastructure called DOCA that helps provide basic infrastructure to use in building operations, in building software or capabilities on top of this. I won't go into details here because I'm about out of time. One of the things that's become very, very useful in terms of performance isolation is congestion control. And what you see, and this is really important in the context of systems where you have a lot of users running. What you typically see in a regular application, in a regular system, is if you're on a single job in isolation, this happens to show some performance data for lamps. And it shows the it shows a fraction of jobs that complete within a particular interval of time for this particular job. So I believe for this job, there were like 75, for this particular graph, I believe there were 75 copies of 75 lamps was run, a particular test was run 75 times, and it shows a very, very sharp distribution. That is, when nothing interferes with it, the performance is very repeatable. However, if you put congestion, introduce congestion into the system, you see a big spread, which is shown in the figure on the right in the times, and some of the copies get down as much as a factor of 2, slow down by as much as a factor of 2. So the data so when it comes to congestion control, there are multiple ways to implement congestion control. The data that I showed you now was done with the HDR or quantum 1 generation of InfiniBand technology, which has a reactive mode for dealing with congestion. So when congestion is sensed within the network, there's the congestion control slows traffic down or speeds it up depending on what's happening in the network. And in that way, it adjusts the traffic so that you eventually get to steady state and get reasonable performance and not start to see network collapse because of congestion. What's coming in the generation that's already coming out now, the NDR generation, is addition of proactive capabilities, where one can use things like round trip times and telemetry data, collect those within the network and use those in modifying traffic control. So at this stage, I'll pass it over to Jitin, that will talk about aspects of Azure as well as some results for the congestion control.
Sure, thank you, Rich. So in this subsection, I'll just focus on like how Azure takes advantage of some of the cool features that Rich had explained before. I mean, not the DPUs, etc. That is not yet there, but some of the other features, and get real good performance isolation. So to start with, I'll quickly give an overview of the 2 different basic classes of HPC SKUs. So the H series, which is, some of you may have seen these slides before, so I'll go a little bit quickly in the previous session. So that's why. So the H series is mainly targeted for the traditional NPI applications, and then the N series is mainly for the accelerator SKUs. The VM name, if it has an R, then that indicates the RDMA support. So let me quickly go to the next slide. So let's quickly take a look at, what are the different challenges in getting the real performance isolation, right? So it could be, we should get complete isolation with respect to, say, CPU, memory from the host. Because, okay, these are the VMs running on the host. So there could be a hypervisor running on the host. There could be a host OS operating system. The different host agents which coordinate the VM deployments or rollout of different agents or updates, etc. So all those things can happen. The next one could be isolations from other VMs on the host. So for example, I mean, if the host is being shared, but at least in case of yeah, maybe in case of Azure HPC VMs, right? So we always have one VM per host. So at least that challenge is not here. And there could also be, I mean, you should also get isolation from other guest agents, right? So we are inside the VM, but I mean, there could be an agent, the other agents running on the VM. For example, the monitoring agent monitors the VM activity. There could be like agent, other guest agent which coordinates with the portal, like for example, resetting your SSH key or password, etc. Right? So those kind of things. The main other one is the network isolation. I mean, that's Rich also had pointed out this earlier, right? So, I mean, in public clouds are like multi-tenant environment, like there could be other customers using that, or maybe like the same customer may have like different jobs, etc. So, I mean, it could be, I mean, you should really have isolation from all those aspects, right? Yeah, next slide, please, Rich. Yeah, so I mean, let me quickly give a brief overview of how we achieve these things. So CPU, in terms of CPU isolation, we have something called min root and CPU groups. So min root is something that is that say allows that configures that the host or the hypervisor should use only these number of cores or these specific cores. So all the activity for the host agents or the host operating system hypervisor, everything are targeted to those particular cores. So in this diagram on the right side, so the light blue color one for in every NUMA node, so that's the Hyper-V partition that's configured using WinRoot. And the rest of the cores, we group it as CPU groups where we tag that to the VM. So VM can only use those cores. So that's how we achieve the CPU isolation, and we have like one-to-one pNUMA vNUMA mapping. So whatever the NUMA node that the VM gets, it's actually mapped to the correct physical NUMA. So we get like consistent performance there also. So I mean, on the right side, I have like two different SKU how it is, how the architecture is laid up. So it's shown there. And on the memory side, we have something very much similar to the CPU partitioning, like we have something called memory partitioning. So we define, okay, these are the memory areas that the VM should achieve. So that can avoid the memory fragmentation, etc., and like get good memory bandwidth, etc. And again, like the network isolation. So I think like we can partition this into two, like network isolation from the host and network isolation from other hosts. So other customers, right? So from host side, okay, since the network or the IB devices are attached as our say SRIOV, I mean, it achieves like full bypass, and then I mean, the VMs can really do the host RDMA or GPU direct RDMA and get the peak performance. So in the previous, I mean, on Tuesday's talk, like we went over some numbers, so which clearly shows that, okay, there is no host overhead and we are achieving close to the peak performance, right? Yeah, and let's focus a little bit on, so the different guest agents, right? So how we can achieve isolation from the different guest agents. So in our HPC images, like we have, these are really optimized images, and we have like fine-tuned configuration for the different agents, everything. So I mean, they are, I mean, they won't use much of the CPU cycles, but in case, say, there are some extremely sensitive workloads, we even recommend to disable the guest agent during the workload and then enable it back afterwards, right? So quickly some pointers on the different HPC images and the different pointers to the configuration, etc. Next slide, please, Rich. Yeah, so quickly, I just wanted to show some quick slides. Rich mentioned congestion. That's a big one, right? So these numbers are from GPCnet using three. As you know, many of you know, like the GPCnet has three different benchmarks: the two-sided latency, bandwidth, and then the reduce, right? So we have two sections, like one with CC disabled and CC enabled. And on the y-axis, we have the congestion factor. So as we can see, like the average numbers are very much close to congestion factor 1, so which is what we really want, right? So congestion control is really helping, and this is really important, especially in case of cloud, where multiple tenants are utilizing the cluster, right? So avoids congestion, improves tail latencies, etc. And again, like as Rich was mentioning, like the impact of adaptive routing. So we went over this diagram quickly in the previous session, but again, quickly, the main highlight is that, okay, this could be, there could be a single job. The communication transfer could be using the same links if it was, say, static routing, and that could really impact the application performance, right? So the blue line here, that indicates without adaptive routing. So we could see like the performance, the link was congested, and then we are not getting the peak bandwidth, right? The nickel bandwidth. But when adaptive routing is enabled, like it sprays the packets into different links, and then we can get close to the peak performance. So yeah. So this, I would like to focus a little bit more on this slide. This is the core, I would say. So here, Rich showed these results on another cluster, but again, these are the results taken on Azure cluster. So here we have three different applications: LAMPS, Incompact 3D, and WASP. We have a histogram of the runtimes on the leftmost side, where there is no congestion, and we can see, okay, we have a constant, peak performance in most of the cases, and then slight variation for some of the other jobs. And it's the same trend for almost all the cases. But in the middle graph, when we introduce congestion, right, so we can see that the performance is all around the place, and it's the same trend for all the three applications. Now on the rightmost section, we have now congestion control enabled, and we can see that with say artificial congestion and with and without congestion, like we can see the application performance is very much close to what it was like before the case, right? Before any condition. So that's the beauty of, that's real performance advantage with this. So with this, let me conclude. I would say that supercomputer on cloud is actually real. We see Azure HPC landing on the top 10 or top 500, top 17 on Graph 500, and even the MLPerf results were out today, and it is very much in line with the bare metal NVIDIA performance. And InfiniBand IB features, right? They really enable cloud native supercomputing, and we take advantage of that. And the good thing is that the HPC on cloud like really makes it available for everyone, right? So that's a clear advantage. So with that, let me conclude, and we could take any questions, Rich and myself.
So thank you. Are there any questions? I see some questions in the chat with Pasha. Do you want to ask them? Okay.
What network? Yeah, it is pure IB, Pasha. Yeah, what cloud, Azure cloud instances use? It is this one. So how many containers VMs per node? Yeah, that is one again. So yeah. So only one VF is exposed per host, and that VF is completely assigned to the VM. Does that clarify, Pasha?
Yes.
Cool, thanks.
This was one question for each round. Across all the NVIDIA stacks that were referenced, where you see excellence? There's like many names were floating: Magnum, Doka, I know Moffett. So
yeah, UCX is part of is packed. Doka is a package, and UCX falls.
I think we lost you.
So UCX, I mean, Doka is a package, and UCX is one of the is packaged under Doka.
And Magnum IO is another thing, or?
To be honest, I can't remember if Magnum IO is packaged under Doka or if it's separate. I don't know.
Is it Magnum IO like new brand for Moffett, or it is?
No. Magnum IO is really a storage support around GPUs, and Doka is really a packaging mechanism, a mechanism for bringing together a lot of different pieces for easy installs and management and stuff like that. And so I just don't remember. I just don't know.
Okay.
Where Magnum is sitting. Yeah.
So, and Jitin, question about SRV. So you mentioned essentially you support single VM instance per machine, right?
Correct. Yes.
You don't really take advantage of SRV.
I mean, we take advantage, yeah, in terms of, like, say, exposing all the features directly, right? I mean, with full bypass.
Okay.
Yeah, I mean, the main ideology why we don't want to say allow multiple IB or multiple VFs per VM is that, I mean, most of the jobs are, say, scale out, right? So I mean, if you want to do that, then why not really scale up on the same single node itself, right? And then scale out. That was the main ideology there.